Okay, I think we're ready to start then. First, before we start the lecture, last week we had a lab. A few weeks ago we discussed what you would like to see changed in the labs. What are your thoughts on how we did last week's lab? Anything that you still feel like was lacking? Okay, so for future iterations of the course, we're going to try designing the labs more in that type of way. This year, we're not going to have any more labs. As you can see, we're here. Where are we today? Oh, we're here today on the 14th. So we have, with today's lecture, we have 3 more lectures total this week, or today, and then 2 lectures next week. Afterwards, we're going to be starting with the presentations. So if you haven't started yet, get started on that soon. All of you should have your topics by now. There is an assignment released on Gradescope for the presentations. There's an assignment released on Gradescope for the presentations. This assignment is due this Sunday. It's a very short assignment. You can do it with your partner. Just give us 4 to 5 sentences explaining what you intend to do during your presentation. Just get that submitted. Should be 10 minutes of work at most. Explain, if you're doing a demo, explain how you plan on setting this demo up, what topics you exactly want to cover, just a bit of like what you plan on doing. Okay, so as I said, we finished our heap topics last week. We're going to continue with Kernel now. Any questions on heap before we completely move on from it? Okay. Project 5 was released on Tuesday. It is due date is on Gradescope. I'm not exactly sure what it is right now, but it's on Gradescope. Challenge 1 and Challenge 2 are 2 heap challenges, one on the Tcache group technique and one on the House of Force. Challenge 3 is a kernel challenge. This time, the first challenge of the semester where you're not going to be doing any actual exploitation, but it's a development challenge, probably a bit more similar to what you might have been used to from your other courses. In the third part of the project, you're just going to be implementing some very simple read and write syscalls. These don't have to be good, they just need to be able to read and write to a file. And there is a reading attached that you should do that's going to explain how this should be done. Don't copy paste the code from the reading, go through it, understand what it's trying to tell you, and then implement it yourself. It shouldn't be more than 10 to 20 lines of code overall, maybe 30 to 40, but it shouldn't be very hard. We're also going to start talking about kernel stuff today in the lecture. Also, we're going to be releasing another homework, either today or tomorrow probably. Short homework, multiple choice questions probably. This is going to be on Moodle. Any questions, organizational matter-wise? And Stephen's office hours today are canceled, so if you have any questions, come to me after class and I'll try and help you. But no projects or Project 5 is still a bit out, so I hope we should be good on that. Okay. Everyone fine with moving on then?
No.
Okay, cool. So today we're going to be talking a bit about how the Linux kernel works, and I don't think we're going to get to any security about it, but we're just going to talk about how it works for the most part. If you've taken 377 operating systems, a good bit of this is probably going to be a review for you. If not, we're going to try covering at least a good bit. We're definitely not going to get through everything. This has entire courses on the topic. UMass has 2, 377, and 577. If this interests you, probably take those courses. Project 5 ongoing. Homework will be assigned today or tomorrow on Moodle. And yeah, today's content, short introduction. Then we're going to talk about 2 different kernel design philosophies, how kernels implement protection, syscalls, the boot process, and we're going to talk a bit about device drivers. So first of all, what is a kernel? It's pretty much the most central part of the operating system. So your operating system, many of you are probably using Mac, Windows, Linux. The kernel is pretty much the most central part of this. It handles the interaction between hardware and software. So your operating system might come with some extra things such as libraries or graphical user interface. These are not part of the kernel, but they are part of the operating system. The kernel is pretty much the most central part that handles the things that a computer could not run without. Usually it manages memory, networking, file systems, processes, and device drivers. And it pretty much acts as an intermediary between programs and hardware. So looking at this example, or at this small example, it's just a line of Python code called open on, this is not an open syscall, this is Python's library function open on file.txt and readable as bytes. So if you're coding your application in Python, you don't, so have you heard, who has heard about file systems before? Cool, that's most of you. So there are different file systems that can be used. Linux, for example, commonly uses ext4, Windows uses NTFS, many USB drives use something called FAT. And these vary between different systems. Linux, for example, it comes natively with one, but it also supports many other file systems. And if you're writing your high-level application in Python, you do, for example, you do not want to worry about how this file system works. Because different file systems have different implementation. They have different metadata and tables that point to different areas, how the files are set up. And when you're writing a program, you do not want to worry about parsing this manually or even using libraries to do this. So instead, this is handled by the operating system. So for example, when you use Python's openfile.txt call, the operating system might check, first of all, where on what type of file system is this file located? Is this .file.txt maybe from your USB stick that uses a FAT file system, or is it from a partition that uses an ext file system? So it's first going to check that, and then it's going to note which driver is responsible for handling this sort of file system, and then it's going to call this driver, which then handles the actual open call. We've kind of talked about a bunch of words here that we haven't really covered yet. For example, a driver. This is usually kind of like a plugin for a kernel that describes how you can interact with a certain piece of hardware. For example, your keyboard, your mouse, HDMI, USB, all of these have separate drivers that specify how these devices should be handled. For example, when you have two different USB sticks with different file systems, they have to have different drivers that can handle these two different devices. Same with an HDMI cable that has a very different protocol than USB, for example. This is why, for example, in Linux, Windows definitely as well, most of the kernel is actually not kernel, but drivers. I think in Linux, about 60-65% is just pure drivers from the source code, which is currently about 25 million lines of code total. So it's quite a bit. Windows is probably double or even much more. I'm not exactly sure because it's not open source, but it's a good bit more. Any questions this far? Yeah.
So every time you plug in like a new keyboard or something like that, the driver is already on the operating system, or?
So it depends. So the operating system comes with a lot of drivers, so it can support a lot of standardized protocols and devices. So if you have, like, for example, a standard mouse or keyboard, your operating system probably already has a driver that can handle it. But if you then go and buy like a $200 fancy Razer mouse that has 20 extra buttons, your kernel probably does not have a driver pre-installed that can handle this mouse setup. So in that case, the mouse often then might come with an additional driver that you need to install to handle this specific device, for example. So, yeah, does that answer? Okay.
Do the drivers come preloaded on the devices, or do you have to like download them?
That depends on the device, I guess.
So if they can come preloaded, can you like load some malicious drivers so that the operating system isn't?
That's actually, for example, Razer mouses, they require a driver to be installed, and this driver has to be installed as the root user because you can't load drivers into your kernel without the root user or on Windows administrator. So with any Razer device, you can load malicious software on it. If someone plugs it into their computer, you have control of it. So hardware or physical access to something is pretty much always security done. Any other questions? And if you're interested in learning more about how file systems work, for example, you should take Ryan's forensics course that goes a lot deeper into how these different file systems are set up and how they actually function. Yeah.
Is the kernel made for the operating system, or is it the other way around? So like, does the operating system say, I want this file in the, or not the kernel, the driver, like to the driver, and then the driver finds the file, or is it like where the operating system goes, okay, this is what this driver is telling me how the file system is set up. Let me get into it specifically.
How exactly, we'll cover that in a bit when we talk more about device drivers, actually. So with that, just wait a few minutes, we'll cover that in a bit. Anything else? Okay. This is a lot, and if you haven't taken 377, this is a very quick summary of a lot of things, so if you get confused, just ask questions. I've tried to kind of summarize it in a way that makes sense, but it is a lot of content. So on microkernels versus monolithic kernels, monolithic kernels is what you're used to when you're using Linux or Windows. It's pretty much that the entire operating system runs in a single address space. So this means that device drivers and all file systems, all of these things are all inside of one main kernel that's loaded. This has the disadvantage that if there is a bug in a device driver, for example, this means that the operating system is fully compromised. Because they all run in the same privilege level, they all run pretty much the exact same process. You find any bug in any of these parts, you have complete control over the system. And this is bad because drivers contain 60 to 70% of the actual OS code, and they generally contain about 3 to 7 times more bugs on average, which is mostly because these drivers are often written by private companies that may not, and not the experienced kernel developers that work on the actual core Linux kernel. So you're often very buggy, especially if you look at Windows, which is completely closed source. You can often reverse engineer one of their drivers for a couple of weeks, and you'll probably get a Windows kernel CD. Then there's microkernels. They are basically designed in a way where so that they're based on a design where you have a small kernel that implements the most core functionality that needs to be at the uppermost privilege level, and then everything else you implement at lower privilege levels, for example, user space or even things between user and kernel space. Advantages, they're more reliable, easier to expand, and if there's a fault in the driver, it probably will not compromise the entire system, for example. And some disadvantages, however, is that since everything is separated, there have to be some communication protocols in place for the different parts of the kernel to communicate. So, for example, the kernel then sees, okay, this call needs to be handled by this device driver, then needs to make a call out to that device driver, and that's much more expensive than just making a simple function call, which would otherwise have to be done. So, most major operating systems that you use on your computers are pretty much always monolithic kernels. When you use embedded systems, they are still very frequently microkernels. But yeah, this was a very big discussion when operating systems were still in full development or very new. I believe it was between Linus and Tannenbaum or something were the two main ones. They had very lengthy discussions about which kernel design philosophy is better. In the end, for computers, or at least for these home use computers, monolithic kernels pretty much entirely won. Okay, talking about protections. So there are several privileged actions that programs can take or that programs have to take, but you do not want them to be able to just do it on their own without having to ask for permissions. Those could mean, for example, addressing I/O or instructions that manipulate the state of memory, or dealing with interrupts, or even halting the entire machine. You wouldn't want your hello world program that you run that has an infinite loop in it to suddenly halt your entire machine, for example. So, or have access to an instruction that would halt the entire machine if it was a malicious program, for example. So kernels handle this by using different protection levels. In the case of monolithic kernels, so this is usually displayed in terms of rings, kind of like that graph showcases. In monolithic kernel design, there are only two rings that are mainly used, ring 0 and ring 3. Ring 3 is where the kernel runs. It has full unrestricted privileges. And then there's ring 0, which is the user space, which is very restricted. All the exploitation we've done in this course so far has been user space. And with the kernel space, we're going to start talking about more kernel space exploitation. That would give you, this is pretty much root access, I guess, in terms of Linux words. And then there's the microkernel. This actually has potential to implement multiple rings. In most implementations, it actually only implements 3 rings and not 4 as displayed here. You have your user space, which is very restricted, again. Then you have your kernel, which is completely, or the main kernel in ring 3, which is completely unrestricted. And then these two are usually combined where you have drivers, I/O, interrupts, maybe sandboxes for certain frequently vulnerable drivers, and so on. And this pretty much means if there's a bug in one of these drivers, you do not have unrestricted access about the kernel. And I believe one of the professors or one of the people that actually researched this topic and came up with these protection rings used to be a professor at UMass. I believe he has, yes.
Bob Grimm, go ahead.
I believe he has since passed away, but
He did.
yeah. But yeah, this was actually invented here.
I'm not sure about that. I think he was at IBM or something,
Okay.
or Bell Labs. But
Oh,
this guy,
yeah.
it was this guy Bob Grimm, and he used to teach the assembly course here, and he was like a weed out course. And then after he retired, he was just the nicest guy, and he was like this avuncular guy, and was around for a long time. He died like not that long ago, like I think before the pandemic, like just before the pandemic or something. But yeah,
Wait, we had an assembly course here?
it used to be required when I got here in the early 2000s, and there was a big fight to remove it because it was hard to understand like why. There was an argument like we don't teach chip design. Why are we teaching assembly? Like, where's the limit, right? And now, the argument is like, why do we even need everything we teach in computer science, right? Like, why, it's such a large, you know what I mean? Like, all the things that required of you all. Sorry to get 10 more seconds. Like, there are other majors within computer science. So it shouldn't have to be so monolithic, and that's the reason why you have 8 electives and just 311, because we decided that was the one thing that everyone needed. But then we also created the BA, of which there are like 13 BA students. But we thought it would be like just as popular. That was even more free-forming. Yeah. Now things have swung back. Like you all want to know assembly something.
We did the scoping. Imagine we had that for this class.
I took assembly. That used to be like a thing you had to do. Okay, sorry.
Yeah.
Maybe I just didn't misheard it, but like, what is exactly the sandbox for drivers?
So a sandbox in the context of computer security is pretty much when you wrap something that has the potential to be vulnerable in an extra protection layer. So if an attacker gets access to it, they're not on the actual system, but inside of the sandbox. And they still need an extra bug or exploit to break out of the sandbox onto the actual system. This is, for example, very frequently used in browsers. For example, browsers have the render process, which is which its purpose is to parse JavaScript and emit output to the screen. And as you can imagine, parsing and executing JavaScript has a lot of potential for vulnerabilities. So this is a process that is very frequently exploited. So browsers, for example, place this process in the sandbox. And if someone actually finds a bug in the browser engine, they're still just left inside the sandbox and not on your actual system. So they can't access your files, they can't access anything. And at that point, they still need to find a bug inside the sandbox before they can get access to your actual system. And these usually kind of just filter out all the communication going out of the driver, and yeah.
And I'm guessing the sandbox is implemented by the OS developers rather than the driver developers. So it's like less prone for like.
Maybe not the OS developers, but it's usually one general sandbox and used for many things, so it's less prone to bugs.
Would it be right to think of it as like a Docker container almost?
Yeah, I guess.
I was going to say a lot of this goes back to like Docker and Kubernetes and all this. This is like the core of the thing. I don't know much about this myself.
A lot of people think that the future of security is pretty much to just sandbox everything, which honestly I think is a pretty good approach. It has performance implications, but they can mostly be mitigated at this point. But yeah.
So, like, I learned that, like, in, like Linux, for example, right, it's like when you make, like, something like a syscall, right, you go from user mode to kernel mode, right? So, like, how does that kind of play in, like, are there more, in Linux, are there more than 2 rings? Like,
in Linux, though, Linux is monolithic, there are these 2 rings.
okay.
So if you use a syscall from user space, it goes to kernel. I think syscalls are the next slide I'm going to talk about more. But yeah, in terms of these microkernels, it would then be completely different. There are multiple interfaces, and that depends on how the kernel is implemented. Yeah.
You mentioned that it's consensus about security is maybe just sandboxing everything.
Yeah.
Wouldn't that suggest almost shifting over to a microkernel approach where everything's all compartmentalized?
Yes. I'm not 100% sure on all the aspects of the arguments of microkernels versus monolithic kernels. This decision was made a long time ago to use monolithic kernels for computer design. And that's kind of how the Linux code base has grown, and that's kind of what is the norm now. But yes, microkernels do have many advantages, especially when related to security, which now that performance has increased this drastically since when this decision was first made, is now becoming a much more reasonable approach. If it's actually going to happen, I don't know, but at least when it comes to the web, for example, a lot more things are starting to get sandboxed one after another. Yeah.
Is there any like modern system that uses like microkernels that are like widely used, not just
Embedded systems, I would say. They're very frequently designed in microkernel architectural approach, especially when security becomes relevant. Thank you. Okay. Anything else on this so far? Okay, cool. Yeah. So now let's talk about syscalls. So how do you actually swap from these rings? Mentioned earlier that user process still want to be able to do protected operations such as I/O to read from a file, for example. You don't want to allow a user process to just do that because it is a privileged operation and it can be malicious. So instead, a user process makes use of something called syscalls on Linux, where it basically asks the kernel for permission to do something. So, so on x86, you have used syscalls before, I assume, and you've had projects where the goal was to launch the execv syscall to spawn a shell, and you did that by setting the RAX register to the syscall number, and then you executed the syscall operation, and this then executed the syscall. So what actually happens when you execute a syscall? First, the register and stack state is saved. Then the privilege level switches to ring 0. Then the syscall handler routine is engaged, which depends on which syscall you're using. It's going to be a different one. Then the stack and register are restored, and the privilege switches back to ring 3. In the next lecture, we're probably gonna actually look at how that actually looks. We're going to be attaching a debugger to a kernel and walking through a syscall. Then you guys should see that in an actual use case. When we're talking about user space programs, so if you're writing C code, for example, you don't usually use syscalls directly. For example, when you use fwrite, fwrite is not a syscall. This is a library function provided to you. So when you call fwrite, it goes into the libc library function, and then in this fwrite function, it then might call the write syscall. To be honest, it probably has like 5 more functions that it's executing for the actual syscall. So this write goes to write 1, write 2, whatever. They're not called write 1, write 2, but there are a lot of different layers between when you execute a libc function and actual syscall. But in the end, this then calls one of these syscalls. Any questions on this? Okay. So this is not really relevant to the exploitation process, but let's quickly talk about how the boot process looks. So first, when you first launch your system, a small program is loaded from the BIOS, and this is, I believe, run. And this calls the master boot record, which is also referred to as the stage 1 bootloader. It has it's stored at the very beginning of your partition, and this is 440 bytes big, and it's pretty much just responsible for searching for another partition and then loading the code that's located there or another area. And this is usually where the bootloader is located, also called the stage 2 bootloader. And this then has a lot more space than just 440 bytes, and this then responsible for example, if you have multiple operating systems on your computer, you can use that to choose which one you want to load. It actually loads a small miniature file system, which it uses to read configuration files that it needs to load the actual kernel. So, for example, if you want to specify if your kernel is supposed to have ASLR or not, you can list that in these configs. And this bootloader is then going to create a virtual or fake file system in memory and use that to read these files out. This is not your actual file system. But again, this then uses this to parse the config files and then it launches the actual kernel. This then mounts the actual file system, it detects the hardware, it starts the init process. Then the init process is the first process in the system, which on many Linux distributions such as Ubuntu is systemd. And all other processes that you launch are then descendants of this first process. And this init process then starts running a bunch of services from the /etc/rc.d/rc directory. This then contains a bunch of launch scripts that can be specified depending on the options you loaded your kernel with, and it starts running them. These can, for example, be networking services, an SSH service, and so on. We can look how this actually looks. So I believe I showed this in one of the past lectures. But for example, if we look at the actual process tree, this showcases how the processes in your system are currently laid out. So you have this absolute parent process, systemd. And actually, I don't see it there right now. Okay, whatever. So this process is the very first process that's launched, and then it starts executing a bunch of different services that are required at the start. In this case, it, for example, also launched my shell, which then launched Zoom, for example, and launched Discord, and so on. And going back, we also said that there are these init scripts that it runs. These are, you can also take a look at them. So here you can so you can see here that there are actually multiple RC directories, RC0 to RC6, and these actually specify different run levels. So when you run your kernel, you can specify different run level, and each of these directories then has different scripts in it that do different things. These could be different protection levels. These could be how your some messages are handled, and these are then specified. Each of these directories then contains a bunch of files that, for example, in this case, pertain to maybe Bluetooth or my window manager or Docker or some VPN stuff and so on. Does this make sense about the boot process? We're not really going to need it for anything we're doing, but I think it's just kind of interesting to learn how your computer actually starts when you launch it. So I decided to include it. Yeah, any questions on this?
Okay. So one question would be like, how would you introduce? Are there any computers that have like a tamper-resistant process here? Like the closest thing I can think of, some PCs actually, I guess all PCs maybe not Macs, have like a lock in the back that would prevent you, from really opening it. But what about like chip level? How could you really protect it? Is there any way? I'm
not very familiar with how your home computers handle that, because I've not really looked into hardware hacking in terms of laptops at all. In terms of embedded devices, something that's very frequently used as secure boot, for example. And when that is used, there's, for example, your entire drive would be encrypted. And when your processor has a little bit of code on the actual processor, and when you first load it up, it uses, this code gets launched, and this code then retrieves an encryption key and uses that to decrypt your drive before it's actually loaded. And this, for example, means that if an attacker goes and tries to desolder the flash and read out the firmware that's on the device, they're just going to get a bunch of gibberish because they don't have the decryption key, they don't have the actual decryption routine that's used. This is fairly popularly used. Consoles, for example, take this very far. Modern consoles, they try to make it very hard to actually extract the real firmware, and at that point you need to get into several hardware level attacks, such as fault injections or power analysis. If you're interested in these, you should probably take 590J. But those are then pretty much focused on, for example, analyzing the power generated by a device while it's running to then reason about the encryption key that might be used, for example, and things like that. Yeah.
Does run level, to some extent, dictate privilege? Because I noticed that Bluetooth is at run level 0, which means that...
Oh yeah, all of these are launched at root, as a root user.
So isn't Bluetooth like very easily exploitable then?
depends. If your Bluetooth driver has bugs, then yes. Which, for example, the Windows, or both Bluetooth stacks of both Linux and Windows have had very many vulnerabilities in the past.
That's nice.
Yeah.
Where is the privilege level like stored on a machine?
There's a specific register, I think it's called RC4, and this holds the current privilege level. It was either set to 0 or 1, depending on what privilege you're usually on Linux, or 0 or 3, I'm not exactly sure. But this holds what privilege level you're currently on, and the only thing that can edit this is the actual kernel. I guess we should probably talk a little bit about how the scheduler works. I didn't include it in my slides because I didn't mean to cover it because it's kind of an extensive topic that 377 spends like half its course on. So your Linux system, if you looked at the process tree, for example, or just in general, there are a lot of processes that are currently running on my system, like a lot of them, a lot. And if you look on Windows, it's even more. So how is this handled? So my machine, for example, has 16 cores, and those were a couple of hundred processes. How does that even work? So this is where the scheduler comes in the kernel. It pretty much decides when a process is supposed to be run, and it also decides when a process is supposed to stop running. So there are different approaches that have been taken to this. The one on Linux pretty much assigns a priority to a process, or I'm just going to summarize at a very, very shallow level. It assigns a priority to a process and has all these processes in kind of a queue. Let's say it's a priority queue of some sort. In reality, there's multiple different queues and many different priority levels and so on. It chooses a process from this queue, and this process is then allowed to run. This process then runs until one of two conditions are met. Either it makes some I/O operations, which might be invoking a syscall, might be trying to read from a file, so on. At that point, the control is transferred back to the kernel, and this process is descheduled. Another way how a process might get descheduled is if it's run for a certain time slice, you then tell the process you've run long enough, get back to the back of the queue, and the next process is then run. In reality, there are a lot of different metrics that are decided how these processes are scheduled, in what order, what priority they have, and so on. But this is kind of the very general idea of this. Yeah.
How fast does the computer switch processes? Like, how fast can this be done?
If you want actual numbers, no idea. Context switching is expensive, though, especially when it goes from user to kernel level, or even in general. So whenever you do a process, so the kernel has a data structure that it maintains for every process. It's a linked list of basically process metadata. And whenever you do a context switch, for example, from one process to another process, you need to save this process's state. So its register state, its memory state, all of that, before you can move on to and then you move on to the next process. This is, for example, one of the reasons why libraries are so important. They mean that a process switch can become a lot less expensive because you have these libraries that you do not need to save off every time because they're just shared. But yeah, these process switches are very expensive.
And that also speaks to threads, right? Like none of what you said has to happen if you have a thread. Almost none of it, right? I mean, you're in the same process space. You don't need to switch out to switch to the next one. Or am I wrong?
Yeah, so it depends on the context, I guess.
Mm-hmm.
So if you have multiple threads, they still get replaced by other processes. But when you jump from one thread to another, then yeah, you're not completely
That's what I'm trying to
yeah.
within one thread.
Yeah.
Within the same process.
Yeah, multi-thread is like an entirely different beast in that regard then. But just talking about single threaded processes right now in this context. But yeah, that is part of the reason why launching a bunch of threads is a lot less expensive than launching a bunch of processes. You don't duplicate the entire address space. With threads, you just need to allocate an extra stack for the thread. Or when you talk about the heap, you might give it an extra heap arena, for example, in the libc malloc implementation. But that then depends on how it's implemented on the specific libc or kernel. Yeah, so you have this way how processes are scheduled. So let's say a process's time slices up and the kernel says, okay, you're done, my turn. And the kernel takes control. This is we're going to go into a lot of different topics here. So there's something called interrupts. So when this timer runs out, a hardware interrupt is generated. This hardware interrupt that is then caught by a kernel routine that then sees this interrupt, for example, specifies that a time slice is up. So the kernel scheduler is then invoked. The scheduler then says this time slice is up. I'm going to put it back to the queue, and then puts in the next process. And then it goes to the process that I mentioned earlier, where it then restores the register and stack of the process that it's currently scheduled, and then switches back to ring 0 by setting that register to the user level value. This also works on a single core. You don't need multiple cores for this. So when an interrupt comes in, it's pretty much put above anything else. If an interrupt comes in, even if kernel code is currently running, the kernel code is put on pause, and instead the interrupt is run first. Same with user level processes. There's a lot more to it. Take 377. Yeah. I hope this kind of made sense. If you have any questions, please ask. We are covering a lot right now about how the entire kernel works, kind of. Okay, good to move on. Okay. If you have any questions at any point about anything I've mentioned, just raise your hand and I'll come to you. Okay, so let's start talking about device drivers. So I briefly mentioned them before. They pretty much enable hardware devices to communicate with the actual kernel. Without them, the kernel would not be able to, or your computer would not be able to interact with the hardware at all. So a lot of these devices have their own drivers. When it comes, even like file systems, for example, they have their own driver. They're not an actual device, but they still have, or like they're an emulated device, a virtualized device, and they still need a driver. One common one that you may have heard in the context of security is our printers, for example. They very often have vulnerabilities. Printers have pretty complex protocol, and printer device drivers have had many vulnerabilities in the past. That's why Windows, I believe, completely sandboxes them. And yeah, so mature OSs such as Linux or Windows, they generally provide support for most of the common hardware. And this is actually part of what makes it so difficult to just write a new Linux or a new operating system that might remove a lot of the backwards compatible stuff that might slow down current operating systems. You just need to support so many different devices to make your operating system appeal to the general user. You need HDMI devices, you need USB, mouse, literally so much. It's like hundreds of different drivers that you need to just be barely functional for the average user. Yeah, so these drivers and monolithic kernels operated at ring 0 with the rest of the kernel. And in Linux, they can actually be loaded and unloaded without requiring your system to reboot. So at any point while your system is running, you can just choose a driver and say load it. You need root privileges to do it, but you can do that. On Mac, for example, this is not allowed, at least not by default. You can enable it, but by default, loading arbitrary drivers while the kernel is running is disabled. This means that if you this makes it at least a little lot less trivial to exploit the device, or at least to get complete control over the device by loading a rootkit, for example. So device drivers pretty much set up custom system call handlers tailored specifically to the device they're meant to handle. So for example, if you have 3 different file systems, each file system has their own driver, and then you call read for a file that's stored in one of these file systems. The driver for that corresponding, or the driver corresponding to that specific file system is called, and this driver's read syscall is called. So in your kernel, you probably have hundreds of different implementations of common syscalls, such as read, write, open, IOCTL, and so on. There are a couple of different types of devices. There are character devices, which is what we're going to be, or what you're going to be focusing on for the projects. They're most simple. They pretty much just transfer 1 byte at a time. They're used for most devices. They're block devices. These communicate with drivers through file management subsystems, and they pretty much just usually deal in larger chunks of memory at a time. And this usually means that they become a lot more performant when you're dealing with a lot of memory at the same time. So we actually, or any questions on how drivers work from a high-level perspective before we move on? Okay. So when you're actually writing a driver, you have these two macros here, module init and module exit. In these, you specify the init and exit functions that are called when the driver is loaded into the kernel or unloaded. So when you load a kernel to the driver, at the very beginning, the init function is called. This function is responsible of maybe setting up or maybe allocating memory on the heap for something for data structures that the driver might need. And the exit function, it then performs all the cleanup. It frees the memory that the init function might have allocated, for example, and it's called when the module is unloaded. So if you either manually unload the module or if you shut off your computer. When you're registering, so when you load a driver into the kernel, it needs to be registered with the kernel. Otherwise, the kernel is not going to know that your driver exists. So this is done using major and minor numbers. Each device in your computer has both a major and a minor number. The major number identifies the device type, and the minor number identifies which specific device it is. So if you have two US, okay, we can just look. And using these numbers, a driver can be assigned. We can look at a quick example. So if we look at the dev directory, it contains a lot of different devices. These are all virtualized. And if we look, for example, at the top here, you see a couple of numbers listed here. The first column is the major number, and the second column is the minor number. So for example, if we look at the loop devices, they all have the major number 7, and then each of these has a different minor number. The same if you look, let's see. There are these NVMe devices have the same major number and different minor numbers, and so on. The TTYs, for example, as well. Does this make sense? How the major and minor numbers work? So you can then register your device driver and tell it this device driver is responsible for handling any device that has a major number of 4. Yeah.
I saw on that list, it also treats standard in, standard out, and standard error as devices. Is there any significance to that, or is that just how Unix works?
These are pretty much file streams. So when you, for example, when you use your read or write sys calls and printing to, for example, if you print to standard out, you basically invoke write, or the printf call is in the end going to invoke the write sys call, which writes to standard out, similar to how you would write to a file. So you still need device drivers to handle that, and they specify which file stream will be used to output, for example.
Okay, so that makes sense.
And as you can see here as well, like the standard error, standard out are pretty much just links to the proc directory, and the /proc directory is pretty much, each of these directory entries is actually a process on the system. I'm not sure where we can see the actual process name. I forgot. In here? Yeah. So for example, if we look in the /process directory, each of these processes, or each of these directories here, the number corresponds to the process ID of one of the processes. So for example, if we look at the first one and look at the command line file, this one that specifies that this, for example, this process was launched with /sbin/init/. Somewhere in here I should also be able to see the actual process name, but I do not remember where exactly this was. We can So we can look at the map files file. Actually, needs to be the root user to look at that in this case, because the process ID of 1 is a privileged process that, as my own user, I cannot just read. And if you look at the map file directory, what does this remind you of? Like, what do these look like? Yeah. Hmm? Yeah.
Hash. Those look like hash values, like someone entered them into a hash table.
Not quite. These are actually addresses.
Cool.
So if you see it, this, for example, the 55E, whatever it looks like, might be a code section address, obviously with ASLR applied to it, so it's a bit more randomized. But if you look at the first 3 bytes here, for example, 000, that looks like it's probably, so these are all start of pages of memory, and the /proc directory, it's interesting. It's not actual files on your drive. It's basically virtualized, or it basically just represents how your processes are laid out in memory and information about each of the processes. And that's kind of, and the /proc directory is not an actual directory, but kind of just an interface of how you can parse this data from the kernel. Which, for example, if a lot of tools that print out information or debug information about a process, they actually just parse the /proc directory instead of working directly with kernel APIs, because that's often easier. I think we should be able to just look at one of them even. I wish this wasn't so hard. Okay, I guess. I'll just copy paste this. And we can actually see the bytes of data that are stored in the process memory space of this process and those in that address range. Isn't that interesting? So we can literally just read a file, and we can read it like a process's address space. And that's kind of how the Linux philosophy of everything is a file. Even your process's memory state is a file. Yeah.
So that corresponds to like the page allocated to that process?
Yeah, I believe this is a page in size. Actually, no, this is larger than a page. 52681. Yeah, it looks. Yeah, this is a lot larger than a page. A page would be, I think on Linux is 4096 bytes. This is a lot larger region than a page, but pretty much just a memory region of some size. I guess I could subtract them from another. Yeah, so this looks like 0x 91,000 bytes in size. So it's a lot larger than a page, but I guess, I don't even know if they're all the same size. We could check that, but whatever.
Yeah, I think I saw one that is like 1,000 bytes of size, so I think they're different sizes.
Yeah.
So, if you wanted to do something programmatically with this, is it best to pretend that it is a file and use like Python open, or is there a different like Python library that allows you to mess with these things?
I've never really dealt with them directly. I would probably not work with them. That's because mostly it's harder. You're parsing directories, kind of.
Right.
Most more modern tools use different libraries and models that do it in a better way.
That more directly access the OS structure.
Yeah.
Okay.
This is most how a lot of older tools used to do it, because it was just simpler when the APIs weren't as well documented or well laid out. So it still exists in a lot of tools, but now there are pretty much better ways for most things.
I know I found an example way back when. I'll see if I can still find it, where someone showed editing memory with a pointer, and then there was another example of basically going to its process location in /mount/proc or wherever it is, and changing the memory there.
Yeah.
So I'll see if I can find an example of that, maybe put it on camera.
Yeah, pretty much. Everything's a file.
Yeah.
Yeah, so quick detour, but any other questions? I don't even know what the question was. Oh yeah, we're on standard in, standard out. That was the question. Yeah, any questions on this so far? Yeah.
So I'm sorry, what's the difference between a major number and a minor number?
The major number specifies what type of device it is. The minor number specifies which device it is. So for example, if you have 5 different USB devices registered, the major number is going to be the same for all of them, and then the minor number is different. So the major number specifies which driver handles this device, and the minor number is then used by this driver to kind of know which device is currently talking to it. Okay, and we can actually create fake devices that don't actually exist with the make not command. We can specify a name. We can say it's a character device, major number 55, minor number 1. And this is actually just going to create a device for us. And then we can access this device, and then we can write a driver that and register that driver for this device. And then we can write to that device, and the driver is going to be invoked. So that's actually how the project's going to be laid out. You're going to execute the make not command, and you're going to create a device with some device number and minor and major numbers. And you're going to register a device driver for this specific process that then handles the. And then when you read and write to this device, your driver is going to be invoked. So we can execute this command. Now if we look at the /def directory, we're going to see that we just registered the A device here. Oh, I'm wrong. So we can look at the A device that we just registered. So it's a file in the /def directory. Major number 55, minor number 1, name A device, just as we have previously specified. And now if we currently tried writing to the A device, for example, we would get permission, I guess we should probably do that as a root user. And no different. So we get a permission denied, which is pretty much in this case the kernel's way of telling us that, or I guess I'm not sure why we got a permission denied there. This is the error that we should be getting. So we're trying to write or read out the device, and it's telling us no such device or address. Yeah, so pretty much telling us there's no driver that's responsible for handling this, so it can't actually read this out. Does that make sense? So we didn't just create a normal file in the file system. We created a specific device or a specific file, a device file pretty much. And that device can only be handled if you have a driver for this device, which in this case we don't, so we get errors. Okay, any questions up to this point? Yeah.
How would the OS know then to call the driver for a device here? For instance, here we did cat a device. Would it parse a device, see that this is a specific type of device, and call the corresponding driver
Yeah,
for
it would find the major number of that device and then look up in the table or some data structure to search for the driver that's responsible for this major number, and then call upon that driver to invoke or to handle the device.
Okay, and so here it's basically saying there's nothing in that table.
Yep. Any other questions? Okay. So when you're writing a driver, there are a couple of required structures. One is the CDEF structure, which is used to register a device in the system. And this holds like some information such as the major number, the minor numbers that it handles, and so on. So when you register a driver, you create the CDEF structure, you populate it with the information of what it's supposed to be handling, and load it into the kernel. There's the file operation structure. This structure defines which syscall this device can handle. So you can say, put in this table, for example, that this device handles the open, read, write, and IOCTL syscalls. And if, for example, the cat command probably uses the open syscall and the read syscall. So if you would, if you would want to support the cat command for this device, you would have to implement or add the open and read syscalls to that table, and then write functions that implement these syscalls. There's the inode and file structures. These are not necessary for every driver, but they are very popular. So inodes pretty much represent how files look on disk, while the file structures represent how the file, how an open file looks. So a file on disk in the inode might show things such as the file size, when it was created, and so on. And then the actual file in memory might have some extra information such as where the cursor is currently located. So for example, if you open a file in C and then read 10 bytes out of it and then read another 10 bytes, you're not going to get the same 10 bytes. It's going to move a cursor and then going to read the next 10 bytes on the next read call. And there are also other syscalls such as lseek, for example, that you can use to advance in this file structure, or advance the cursor that might be stored in the file structure, this runtime information. same such as maybe some flags as how the file was opened, if you opened it as read-writable or if you opened it as only executable. This, for example, in the Python command we spoke at the very beginning, where you open the file with the arguments RB, which specifies that you should only be able to read from this file. So that's the flag that would be appended to this file. And if you tried writing to the file structure would say, no, this file, this currently open instance of this file can only be read and not written to. And when you're actually operating with these drivers, there are a couple of commands we should be aware of. First, the lsmod command. This provides a list of the currently loaded kernel modules. So if we execute it, these are the modules that are currently loaded into my kernel, and maybe some names might make sense. Let's see, some IP6 table, a lot of network management stuff, an NVIDIA driver, some GPU driver, Bluetooth driver, and so on. These are currently loaded. And on Linux, drivers are often loaded as needed. So if I, for example, plugged in, if I didn't have an HDMI device plugged in, you would not see an HDMI driver listed here, which I have no idea what it would be called anyways. But then once I plug an HDMI cable in, it would then load an HDMI driver to handle this, if it has one. Another one is insmod. This one is used to load a kernel module or insert a kernel module into the kernel. So after you compile a C file into an executable kernel module, you can use insmod on that executable and load it into your kernel. That's when the init function would be executed, for example, and that's when it would register itself into the kernel. There's also remove mod, which you can use to remove a loaded kernel module. And then there's the dmessage command, which prints the kernel ring buffer. So if I use this here, for example, you can see all the messages that the kernel is currently passing. So in this case, you can see that I have Discord open, for example, and Discord keeps trying to read my other processes to figure out which process is currently open so it can display that to my friends list or whatever. And my kernel keeps telling Discord that this is not allowed and that it was denied, and Discord keeps trying that every second 20 times, and so my entire kernel buffer is filled with Discord.
Why does it do that?
Because Discord usually tries to, so it has like a functionality where it displays to your friends what you're currently doing or something, and by default, the Linux kernel has issues with that, which it should, and so this buffer is then completely filled with, this was denied. So whenever you're trying to do anything kernel related and you have Discord open, you need to completely close Discord, because otherwise you can't actually debug or for example, if you do printf debugging in your kernel, these printf messages would be written to this kernel buffer. So if you're trying to debug a kernel module and have Discord open, you can't see your printf debugging messages. Discord is actually the only application that I've ever seen do that, but yeah, it's very annoying. Yeah. So some extra resources if you're interested in learning more about these. First, there are 2 courses that UMass offers, 377 and 577. 377 is the base kernel course or operating systems course that UMass offers. It's very theoretical, but it does cover pretty much it covers scheduling, it covers virtualization, so how file systems are virtualized, how virtual memory works, and concurrency, so how, self-explanatory. But yeah, that's kind of what 377 covers. It's very theoretical. You're not going to learn how to actually write kernel modules or anything like that, or how to hack on the actual kernel, which I believe is a major downside of it. And there's 577, which is no longer officially offered, unfortunately, but you can still do it as an independent study if you email the professor, and all the lectures are online, all the activities are online, and in that way you can still take the course. This one is a lot more practical. You compile your own kernel, you write extra syscalls for the kernel, you write file system drivers, and so on.
Who's the purpose?
No, forgot his name. The same one that teaches 677. Yes, he teaches this, and yeah, I've gone through a good bit of lectures, not all yet, but 577 seems like a very good course to take if you're interested in that sort of stuff. Then there's a few readings. The first one's actually one from myself. I did a small write-up a while ago. I'm writing a small kernel driver. The driver is horrible, filled with bugs. If you write an actual driver, you should not do it like that. I did not handle race conditions and stuff at all in it, because I intended to do a second part where I fixed those things, and I never did. And there's Linux kernel labs. This is pretty much, I'll quickly open it up, I guess. This is my favorite resource for writing kernel drivers. It has a lot of content on first the theory behind how things works, and then it has a lot of labs where you write character device drivers, block device drivers, file system drivers, networking drivers, and so on. Actually, the character device driver reading, oops, wrong one. This one is actually the reading that's assigned for this for Project 5 Challenge 3, and it kind of goes in depth of how you write a kernel driver, which we're not going to have time to go over in class, but you can probably get through the reading in 20 minutes, and the assignment should not be all that difficult. But if you have any questions about it, feel free to ask me. And then there's the book, LDD3, Linux Device Drivers 3. This is pretty much was the recommended resource pretty much. It's a pretty long book that covers everything device driver related. Any questions so far? Yeah.
So this whole thing though, only for the Linux operating system, if we were trying to write a driver for like Windows or something like that, it'd just be...
Then you would need to learn Windows. So on Windows, a lot of the top concepts we're covering are very similar, but the actual APIs you use, for example, how scheduling is managed, how processors are managed, are very different in Windows oftentimes. So I do not know about Windows resources to write kernel drivers because I don't really care for Windows. But yeah.
There's if you're interested, there's a guy named Mark Rasuvinich, I think, but you can search for the term sysinternals. So he developed, I think, the Windows NT kernel and worked for Microsoft for a lot of years, and then I think left and then wrote all these books on like how it all works. And then he has an enormous number of free tools that are actually also useful for forensics. And then I think Windows like bought his company, which is like a dream, right? Like you leave and then you're back. But I wouldn't even call it a textbook. It was akin to the Unix. There's a bunch of books by like Richard Stevens, who also died. But I really think it's Mark Rasuvinich, and there's a lot of resources online that are really, really good. I've just never delved into it either. It's definitely similar concepts, but like a different world. Yeah.
Windows internal books are pretty much the books for anything Windows related. If you, for example, decide to, one job path you can take with low-level security knowledge, for example, is malware analysis, and then you would probably have these books as a reference, learn how the WinAPI works. So Windows, instead of syscalls, they use their completely different API that works very different in a lot of ways. To dive into these, for example. One thing very relevant to exploitation is number one, how Windows handles processes. So on Linux, if you want to spawn a shell by exploiting something, you can just call binsh and you get a shell. This works both locally and over a network. So even if we had like a server up and you exploited something running on a network, you just have to execute /bin/sh and it would duplicate these handlers to you automatically and spawn a shell. On Windows, that is not the case. On Windows, processes are managed differently. So if you use the Windows equivalent of execv/bin/sh, which Windows does not use a bash shell, so the equivalent will be different. But if you use that equivalent, you would be spawning a shell on the remote Windows server and you wouldn't get anything back. So in Windows, you actually need to write a complete reverse shell, for example, in your shell code or in your ROP chain, which is a lot bigger. Windows shell code is usually around 250 bytes. On Linux, you can get it down to 21, I believe, something like that. Windows also has a lot more exploit protections that have been released in the recent years. I believe one group is doing a presentation where they're going to talk a bit more about that. But in a lot of ways, Windows is starting to become a lot more difficult to exploit than Linux. There's also the thing, though, that a lot of this is optional, and so most programs don't actually have these enabled. So, for example, very recently, I saw an Microsoft Edge developer complaining about that on Twitter, how in their Edge driver or in their Edge browser they enabled all these modern security mitigations, and then one of the AV vendors just loaded a module into one of the antivirus vendors loaded something into the browser that did not have this protection enabled, and that then let an attacker bypass it, for example. So these protections exist. They're very good and very difficult to bypass. Most developers don't use them, though, which makes Windows very hard to exploit in theory, but in reality, often it's very easy. Especially when you look at random Windows kernel drivers written by random people that have never been properly reviewed and are absolutely terrible. Any other questions? Okay, let's look at how one of these drivers actually looks now. So, wait, that's the wrong project. So we're actually just going to look right at the project that's assigned to you. These are the files that you're going to be getting for your project. If we look at the source directory, these are the two kernel modules. Let's look at that will be provided to you. So we have hello.c. This is how pretty much the simplest kernel module you could think of would look. You have your init and exit handlers that specify an init function and an exit function, which my language manager is not happy with apparently, but whatever. So the init function in this case, it just prints out a message, module successfully initialized, and the exit message prints module successfully unloaded. And that's pretty much the entire, that's how simple a kernel module could look. It looks pretty much exactly how your C code might look. If we want to build these, I wrote a small build script that you can use for your homeworks. It asks for the module name as an argument, and then it pretty much just writes a makefile. Actually, you can specify the name, which is source directory hello, and this pretty much writes this makefile, which specifies the name and then executes a make command. This make command, so Linux made it very simple to compile kernel modules, where you pretty much just specify the Linux kernel source code, and and your current, this is my current working directory, and that it's a module, and then the Linux, and then the make file would then look into the source code and go into the Linux kernel's build code to actually just build your module. So you don't need to worry about any complicated GCC flags or setting up a hard make file, or you can't, for more complicated kernel modules, you certainly have to make it a bit more complex, but it can be this easy pretty much to just compile a kernel module. So in this case, it wrote this the build script wrote this make file, and then it removed some extra files that were generated by it, and then it moved the kernel module into the /fs directory. If we look at the fs directory, this is pretty much just a file system. So it has a bin directory, etc, home, init script, and a couple of other directories that you're probably used from Linux. And here it has our hello.ko kernel module. Kernel modules always end with the .ko extension. And does anyone have an idea why we have generated an extra file system here? Or why we have like all these extra, why we have like this file system here? Or what like the purpose of that is, of having of using that? Yeah.
Sandboxing?
Yeah, kind of, pretty much. So we don't want to load this kernel into our actual, or this kernel module into our actual kernel. So what we're instead going to do, we're going to run an emulated kernel environment. We're going to be using QEMU for it, which in a lot of ways is similar to VMware. It's a lot more lightweight, and with it we can launch our kernel in about 10 seconds, or 2-3 seconds actually. So if you crash your kernel, you can just restart it very quickly. So in this case, we have this extra file system. And if you look at our launch script, this starts by, this is a bit of a weird syntax, but it goes through the fs directory and compresses them all into this init.ram.fs file. This is pretty much what QEMU, and then we execute QEMU. We pass it this init.ram.fs. This is kind of what the file system is. And we also specify the BZ image, or the path to it in the Linux. This is pretty much the actual Linux, or part of the Linux kernel binary, or the actual kernel. And we specify some other options, such as, in this case, I told it to not apply kernel ASLR. So in this case, we can just run the launch script. It makes use of the init.ram.fs and the actual compiled kernel binary in the Linux directory here. And it's going to do some stuff, more stuff. And now we have our kernel. We're just in a separate kernel instance right now. If I look at, for example, if I try looking at my home directory, I'm not sure what that was. If I try looking at my home directory, you can see that I'm not in my actual home directory anymore. I'm now inside this virtualized kernel by QEMU. So if you break something in here, it's not going to affect the rest of your system. You can just Control-C, get out of it, you're back on your main system. So launch it again real quick. So we see that we have this hello.ko file now. If you execute the lsmod command to check which drivers are loaded, you can see there are none. This is a very, very minimalized kernel. There are no drivers here right now. Now we can execute insmod on the, if you remember this, is how you insert a kernel module. And now you see that the dmessage or the, so this kernel was actually compiled with a run level that doesn't just print these out to the buffer, but also prints them out to your console directly. This just makes debugging a bit easier. But you could also use dmessage, and then you would see at the very bottom that this module was successfully initialized, which if you remember correctly from the hello.c file, that was the message was supposed to be printing. And if we execute lsmod, we can see that our kernel module was loaded, and this is the address it was loaded at. We disabled ASLR, so it's a nice clean address actually in this case. We can also use remove mod on the kernel module, and we see that the module successfully unloaded. lsmod is no longer there. And that's pretty much how simple it is to load and unload kernel modules. And what I just did is actually the first part of your homework already. You just have to show that you can load a module successfully into the kernel, and it's part of the project. The second part of the project is expanding the simple.c file. It's a little bit bigger, but 100 lines still not that big. It still has an exit function. It has an init function, which does a bit more in this case. And it has the file. So let's go from the top. It has the def data structure, which the cdef here, for example, this cdef struct or this field here, where I'm currently on, it holds the major and minor number. We have the open syscall, which in this case just prints out device open. Has the read syscall, which prints out device read. Write syscall, which prints out device written. Then you have the file operation struct, which specifies that this kernel module supports open, read, and write using the sopen, sread, and swrite functions here that we implemented. The init function is a little bit more complex than what we saw before. In this case, it allocates. It uses the alloc char_def region function using the def struct and a minor number and name of the kernel module. And the advantage of this is pretty much that it dynamically allocates a major number and returns it. So if, for example, if you would use 55 every time, there might be a chance that a different driver already has 55 and it would fail. So instead, the good practice when you're writing drivers is to allocate this dynamically, and the kernel just gives you back a major number. It then does a print k, which is a kernel print, at the current alert level, which is an alert level that specifies what how important this is. There are different levels, and some get printed out to your terminal, others don't. And then pretty much just prints out the command to us, which we should use to create the device for the major number just allocated. Then it sets the size of, or then this def struct, pretty much what you're going to be using to hold the, or to operate on the actual buffer of the device. And it then initializes it using the file operations structure and adds it to the actual kernel in this case. And then prints out module successfully initialized. And during the exit, it pretty much just deletes it and does unregister. This is a lot, and it's a bit confusing, so go over the reading. The reading explains all of this, how this actually works. And if you have any more questions afterwards, you feel free to send me a message. I am going to explain all of this. So in this case, for example, if you wanted to operate on this, I'm just going to do this very quickly. It shouldn't take longer than 2 minutes just to show you how that would look. So we're building the simple dot